This video is going to go through the solution of a projectile motion problem. So here's the question. While delivering toys, Santa Claus slips off the top of a roof. At the edge of the roof, he is traveling at 12 meters per second. From the diagram, you can see that it's a 30-degree slope and that he's 7 meters above the ground. Questions are, how long is Santa in the air? How far from the edge of the house will he land? And at what speed and direction will Santa impact the ground? So here's our basic table how we start. I've got our Vox TVA, VOX TVA, and I've got my vertical list of givens and my horizontal list of givens. So our rule is every time we get an acceleration, we have a list of givens. So I've got one for the vertical, one for the horizontal. Vertically, kind of like free space and bingo. You know it's going to be negative 9.80 meters per second squared going down. Horizontally, there is not going to be an acceleration, so that's going to be 0. So there's not going to be a change in velocity horizontally for all of our problems. Alright, so let me fade out the diagram a little bit so I can draw some things. So here's the initial velocity at 12 meters per second. And what I want to do is I need to break this up into horizontal and vertical components. So I'll start with the horizontal vector at 30 degrees, and then that becomes v naught in the x direction of 12 meters per second cosine 30. So in my column, in the horizontal part, I'll put 12 meters per second cosine 30. Now, because the acceleration is equal to 0, the final horizontal velocity is also 12 meters per second cosine 30. Next, complete the triangle. I've got the horizontal component. Here's the vertical component drawn in. Vertically, it's going to be the opposite side, so it's going to be Vy naught is equal to 12 meters per second sine 30. Since it's going down, that's going to be negative in my table, so negative 12 meters per second sine 30, and the arrow that I've drawn just to indicate that it's going down. The next thing I'm looking at is the distance in there. They tell me that it's 7 meters. So I'm going to use that 7 meters in the x direction. Since I start, wherever I start, I'm going to make it 0. So in this case, it's going to go down to the ground, so it's a negative displacement. So that'll be negative 7 meters down to the ground. Time to look at the problems themselves. So let me squish this up a little bit and get rid of a few things, just so I have some space to write. So what I need to do first is I'm going to find the time. Nice thing is when I find the time, I can find get the answer, I can put it in the vertical and the horizontal columns. So I'll find the time with the vertical given, so I make my little note here saying what I'm going to attempt to do with the math down below. I need an equation with x, v naught, t, and a in it. So the equation I'm going to choose is x equals x naught plus v naught t plus 1f at squared. Putting in my numbers with all the negative signs, it's negative 7 meters is equal to the quantity of negative 12 meters per second sine 30 times t plus 1/2 negative 9.8 meters per second squared times t squared. So make sure in this step you're showing the numbers and the units. Now, a cool little math trick, because every expression that I have here is negative, what I can do is multiply both sides of the equation by -1 and actually use all positive numbers. But I'm not going to do the math trick. I'm going to stick with the numbers that I have here. And what I'm going to do is the quadratic formula in order to solve this quadratic equation. And when I do that, I get two answers. I get t at 0.730, or t is equal to negative 1.96. Time can't be negative, so it's got to be the positive 0.731 seconds. And I'm going to put that in my table over here for time in both the vertical and horizontal. Time's the only variable that we have so far that's a scalar, so it goes in both columns. Continuing on to part B. Part B, I'm going to find the range. To find the range, I'll make a little note telling you what I'm going to do with the math down below, so I'm going to find the range with the horizontal givens. Horizontally, there's only one equation. Range is equal to Vxo times t. That is, the distance I travel horizontally is equal to the initial velocity in the x direction times time. That's the only equation we have horizontally that works. And that's because the acceleration is equal to 0, so this is all you have left. So when I put in my numbers, the horizontal velocity of 12 meters per second cosine and the time I just calculated with all the decimals, I get my range to be 7.59 meters. Final question. Find the vertical final velocity using the vertical givens. So again, I'll make a statement telling what I'm attempting to do with the math down below. So to find that final vertical velocity, I need to find the open space in the vertical column. And to do that, I've got to need an equation that uses my givens above. So I actually have a couple equations I can use. I'm going to choose to use the VOAT equation. V equals V naught plus AT. I'll put in my numbers. V is equal to negative 12 meters per second sine 30 plus negative 9.8 meters per second squared times the time with all the decimal places. And when I do that, I get the vertical component to be negative 13.16 meters per second. Negative because it's going down. So at this point, I can write it in over here in my list of givens. So now that my table's done, I need to write my impact triangle. So my impact triangle is going to contain everything in this final velocity row on my list of gibbons. So it's going to look like this. Vertically, it's going downwards, and it's going downwards at 13.160547 meters per second. Because I've drawn the arrow going down and I've indicated that direction, I'm going to drop the negative sign. I don't need it anymore. Next, I know the horizontal velocity, and they'll complete it with the impact velocity. So horizontally, it's 12 meters per second cosine 30. Horizontally, the velocity never changes, so it's still 12. And that makes up the two sides of my impact triangle. So now I can find magnitude and direction. Remember, in projectile motion, there are two triangles, one at the beginning, the initial velocity, and one at the end with the final velocity. The final velocity uses the horizontal and vertical final velocities. So at this point, I'm done with the physics. It's time to do a little bit of math. So I'm going to find the impact velocity speed with all the final velocities. In other words, I'm going to use Pythagorean's theorem to find the length of the hypotenuse. And when I do that, I get the impact velocity to be 16.7 meters per second. To find the direction, I'm going to find the angle. So again, I'm listing what I'm attempting to do with the math down below. Because of the way I've drawn the angle with the ground, I'm going to make that the tangent theta is equal to the opposite speed over the adjacent speed in this case. So when I find theta using the inverse tangent or the arctangent function of my calculator, I get 51.7 degrees with the ground.